Okay, good afternoon, AP Calc. This video is being made just in case we run a little bit short on class after our first quiz and don't have time to talk through these completed notes together. So this video will go up on YouTube and you guys can look at it, like I said, if we run out of time going over Unit 1, Lesson 4 live. All right, so this lesson is about continuity. Here we have this way we're going to define continuity. We're going to let our function be f of x. We're going to define continuity at a number. We're going to let that number be x is a. And we'll say the function is continuous if three conditions are satisfied. So the conditions are, 1, that f of a exists. Okay, so we have to have a function value at a, and it has to be defined there. All right. Second condition is that the limit as x goes to a of f of x also exists. Okay, we've talked a lot about already how a limit and a function value are different. Okay, so conditions 1 and 2 are both that the function value exists and the limit exists. The third condition is that, and this is an easy one, 1 and 2 are equal. Okay, so really the function has to be defined at a, so f of a exists. The limit has to exist today, and those have to be the same thing. Okay, if all three of these hold, the function is continuous. The second part says that the function f is discontinuous at a if one or more of these three conditions are not satisfied. So first of all, let's change the no to a not. And if that's the case, we would say that a is the point or the location of discontinuity. All right, and we've seen already this point of discontinuity can produce a couple things. It can produce a vertical asymptote. It could also produce a hole. It could also produce, which we haven't really looked at yet, but what's called a jump discontinuity. Okay, where there's not really a hole, there's a function value, discontinuity. There's not an asymptote, there's not a hole, but there's a discontinuous part of the function there. Okay, so let's get into the types of discontinuities that we'll see. Okay, first one is the limit exists, but the function value doesn't. Okay, and now we're changing our number from a to c, but that's fine. So an example of this could be, let's say that we have some function, okay? It's got a limit right here at x equals c, but there's no function value. So we have a hole at x equals c, therefore f of c doesn't exist, okay? That function is not continuous because it's not defined there. Second part, f of c exists, but the limit doesn't. Okay, so that could be maybe something like this. So I'm going to let this point here, or this value here, be x equals c. This again is our function. Okay, but now I've got f of x jumping and being defined down here. Okay, so the limit, the right-hand limit here and the left-hand limit here are not the same. So the function is defined, yes, but the limit does not exist. Okay, this is also discontinuous. So this is the case that the limit as x approaches c of f of x, d&e. Okay, case 3 is that both exist, but they're not the same thing. All right, so for example, maybe something like this. Here's function f of x. Okay, this is x equals c, but the function is defined down here. So here's the limit of f as we approach c. Here's the function value at c. They are not the same thing. So in this case, we can write that f of c does not equal the limit as x goes to c of f of x. All right. Last case, and this is a little bit tricky, right? So here the limit goes to either positive or negative infinity, but this really implies that there's not a function value there, right? Because positive or negative infinity isn't really a finite value. So in this case, we're going to have a a vertical asymptote. So could have, say, a function that looks like this. Okay. So really, you could say here also f of c doesn't exist, but the limit as x goes to c does. All right. So really, those are the four types of discontinuities that we'll see, right? Just going over this again. Function value doesn't exist. Limit doesn't exist. Limit exists. Function value exists, but they're not the same. And limit exists. Function value doesn't exist, but because of an asymptote. All right? So now we can define this a little bit more formally. We can say a function f of x is continuous on an interval now. So a closed interval a to b. If it's continuous at each x value in the interval, and now because this notation means you have some interval a to b, right? And it's closed, which means it includes those two endpoints. All right? So the function is continuous on the interval if it's continuous at each x value in the interval. Okay? And we're gonna add these two conditions for the endpoints. So at x equals a, we'll say that the limit as x approaches a from the right of f of x is equal to f of a. Okay? We can't say the total limit because we don't know what's going on to the left of a. And then the other condition is that, and you can probably figure this out, the limit as x goes to b from the left of f of x equals f of b. So basically this is a technical way of saying that at these endpoints, the one-sided limit equals the function value. Right? We don't really know what's going on with the total limit at a because we don't know what's going on the left. And we don't know what's going on with the total limit of b because we don't know what's going on to the right. Okay? So I just need to add in that this is the condition at x equals b, and then that's how we define continuity on an interval, rather than here we're defining continuity at a point. Okay, so for an open interval a, the one-side limits aren't required, and that's because, right, and sorry, I'm going to make one more change here. I just want to be totally correct. This is the function f. So at an open interval, right, the endpoints are actually not included in that interval, so we don't need to bother checking the endpoints. As long as this condition is met, that the function is continuous at each value inside the interval, then open interval, this is okay, because we don't care about a, we don't care about b. All right, 2 examples, and then we will conclude just this video. All right, example 1. What are the points at which the function is discontinuous over the open interval 0 to 5, right? So if we go from 0 to 5, not including 0, not including 5, when is this thing discontinuous? Use limits, right? And the definition of continuity to explain why the points you found are discontinuous. All right, first problem I see is at 1, right? So at x equals 1. Now, first, the checklist is the function defined there? Yes, it's right there. The function value is 3. Does the limit exist there? Yes, the limit's right there. It's 1, but they're not the same. So we can say that, let's call, just to make this easier, let's call this function f of x, right? So f of 1 is equal to 3. The limit as x approaches 1 of f of x is equal to 1, but 3 is not equal to 1, so it's discontinuous. Okay, so this is 1 point. We've got another point at 2, and another point at 4. Now at 2, this is an easy one. At x equals 2, the function value at 2 is, it's not defined, it's infinite. Okay? So automatically, it's not continuous there because we don't have a function value. And at 4, at x equals 4, well, if I look there, from the left side, the limit is 2, right here. From the right side of 4, the limit is 1, so this limit doesn't exist. The function is defined, but the limit's not defined. Okay, so we can say at 4, the limit as x goes to 4 of f of x doesn't exist. So it's also discontinuous. All right, example 2. Back to piecewise functions. So what are the points of discontinuity of this function? Right, it's defined in 3 different parts, and make a sketch. Okay, so if we look at these functions, this is a line, this is a quadratic function, this is a polynomial, right? So we know that all these functions are continuous over their domain. All right, the problem is in this piecewise function, the function is changing, right? So really what we need to check is the transition points. We need to check what's going on at at -2, and we need to check what's going on at +1. Okay? So at x equals -2, well, the function value, f of -2, right, I need to use this top function because that's where x is defined at -2. So f of -2 is -2 minus 6, which is 2 minus 6, which is -4. Okay, so the function is defined there. So far, continuity holds. The next thing is what's the limit as x goes to -2 of f of x? Well, from the right, and I'm going to be a little bit sloppy, so the right limit at -2, the left limit. Let me back that up. The left limit, LL. Well, we know, because we just used this function, that it's -4. Okay? From the right of -2, we've got to use this function. And if we plug in, -2 squared is 4, times -1 is -4, minus 4 is -8. So, got a problem. These two one-side limits are not the same number. So this limit doesn't exist. Okay, so -2 is a point of discontinuity, right? Because the limit doesn't exist there. The other point to check is 1, right? So we'll do the same process. When x is 1, well, what's the function value? Well, the function value for 1 is defined by this function. Plug 1 in there, 1 minus 6 is -5. Okay, so far so good for continuity because we have a function value. Now, when we take the limit as x goes to 1 of the function, well, here we get -5. Here we also get -5 because if I plug in 1, I get -5. Right? So the limit exists, and these are the same, right? i.e. f of 1 is equal to the limit as x goes to 1 of f of x. So it's continuous there. So there's no discontinuity. No discontinuity. So that means that this is our only answer. Okay? And now we can check that graphically. So we'll make the sketch. And bear with me, guys, because this is not going to be the prettiest sketch, I don't think. So top function. Top function is -x minus 6. So that means I've got a y-intercept of -6 and I've got a slope of -1. So if I'm thinking about this right, this thing is going to have intercepts at -6. Okay, now I'm going to have to erase it, but I'm going to plot that point on both axes. 1, 2, 3, 4, 5, 6. So, and it stops at -2. So at -2, the function value is -4. Okay, and that's a filled in circle. So drawing this, that's not too bad. First, our top part of the function looks like that. All right, and let me go to blue. So this is the point, -2, -4. All right, for the second part of the function, this is equal to a parabola, right? Starting at -4 and opening downward. So, and I should say with vertex at -4 and opening downward. All right, so 0, -4. 0, -4 is right here. All right, and this thing opens downward, and it stops at -2 and at 1. So this is going to go to -8, and it's going to be an open circle there. So looks something like this. Okay, this point down here is the point -2, -8. So we see discontinuity there, and it also stops at 1. And when I plug in 1, I get -5. So it's this kind of part of the parabola there, right? And this point here is 1, -5. Okay. Oh, and I need to be careful. Right now, at 1, -5, I should have drawn an open circle. So let me correct that. Okay, open circle for now, because both these values are exclusive, right? How do I get the function value at 1? Well, I use this. If I plug in 1, now that circle is going to get filled in. 1 to the 4th minus 6 is -5. So I'm going to go back to blue. So this circle gets filled in, and it's a cubic opening upward, so you know it's going to do something like that. All right. So the point 1, -5 really gets filled in by that third bottom function. Okay. And then we can see from the graph that our discontinuity analysis in part A is right. So at -2, yeah, we have a non-continuous function, right? We have function defined there, but limit not equal. And limit doesn't exist. Okay. At -1, at +1, yeah, the function changes, but the function value is the same. It's -5, and the limits are the same. So this is interesting. This is a continuous point, but it's called a cusp. So it's a place where the derivative doesn't exist. All right. So that's it for the video. Hopefully it was helpful, and you can get started on problem set 4.